Hi, today we're going to talk about how you can do analysis of a mixture using spectrophotometry. And specifically in this particular video, I'm going to use an example of using UV vis, but you can use any sort of spectroscopy actually. And we'll definitely talk about that as we get into things like infrared analysis. In order to understand how this works, you have to understand Beer's law, which I explained in a different video that I will link below. And basically, Beer's law says that the absorbance of something at a given wavelength is going to equal the molar absorptivity coefficient of that substance at that particular wavelength times the path length that the light travels through times the concentration of your substance. Again, I said this is the absorbance at a given wavelength. And I mentioned that the molar absorptivity coefficient is specific to a particular wavelength. And so what you should understand about this is this sort of linear relationship between absorbance and concentration is only true at a fixed wavelength. So if you're looking at a bunch of different standards and you measure one of them at 375 nanometers and you measure another of them at 392 nanometers, and you measure the third standard solution at 406 nanometers, like you're not going to get this linear relationship between absorbance and concentration. This always has to be at one particular wavelength to get that linear relationship. So let's think about what I just said in a different way. Here I have some sort of colored compound, and I've made 4 solutions of known concentration, and I'm going to use those to make a calibration curve. And so basically I'm going to run this at 500 nanometers, and I get this lovely, very linear relationship that I can use with Beer's law. Now, what would happen if I did the same analysis, except instead of running it at 500 nanometers, I ran it at 525 nanometers? Well, I would get different absorbance readings, and you can see that in the 525 nanometer calibration curve graph, I have a completely different equation for the trend line, including, importantly, a different slope, and we'll talk about why slope is so important later. We even have a different r squared. This is a completely different analysis. So we're going to take those principles that I just explained, and we're going to talk about how we use this to do analysis of a mixture. So here we have a solution of some green dye, and here we have a different solution of a kind of a bluey green dye, and we're going to throw those together to make a green mixture. What we want to do is figure out what the concentration of each of the dyes were in that mixture. So if we had measured each of those solutions before we mixed them together, we might get 2 different spectra that looked like this. And so you can see the bluey green I've called compound A, and the yellowy green I've called compound B. But once you mix them together, you can't measure those 2 substances separately. Right? You can only measure them together, and what you'll get is something that looks like this. Where does this curve come from? Well, it comes from the addition of the 2 component curves. So let's just pick a wavelength, and I'm going to pick 550 nanometers. You could do this with anything, but if you look at component A at 550 nanometers, right, the absorbance of A at that wavelength is about 0.47. I'm kind of estimating on this graph. And then if you look at component B, right, the absorbance of B is going to be about 0.25. And so what I'm saying here is that the absorbance of the mixture is basically going to be the sum of those 2 absorbances, which is going to be 0.72. And if you look at what's there, that actually is about 0.72. Another way to write that is if you do measurements at a given wavelength of a mixture of 2 colored compounds, the absorbance of the mixture is going to be the absorbance of whatever your first compound is, here we're calling it compound A, plus the absorbance of the second component, which here we're calling compound B. So you can see how I use subscripts here to differentiate between the absorbances the absorbance of the mixture, the absorbance of thing A, and the absorbance of thing B. We're going to use a lot of subscripts in this. But there's a problem, which is that if we have a mixture to start with, we can't separate out compound A from compound B to figure out how much there is of each. So what can we do? So we can make a set of known standards for compound A. We can make a set of standards for compound B, and then we can turn our data into calibration curves. So in this case, I picked measuring at 550 nanometers because that's what I did when I was picking a wavelength off the graph. And you can see that compound A and compound B, different calibration curves with different associated linear equations. So what I want to do now is think about the absorbance of each of these components at 550 nanometers. So for compound A, the absorbance of A at 550 nanometers, and again, I'm just going to take Beer's law, I'm going to plug in what I know, is going to be the molar absorptivity coefficient at 550 nanometers times the path length the light is traveling through times whatever the concentration of A is. Now, if you look at this graph, we have an equation for our calibration curve for compound A, and you'll see it in the format y equals mx plus b, which is the way Excel always spits it out. So let's think about what that means. Y is, what is that? Well, look at the y-axis. Y is the absorbance, right? So that's our absorbance. And so that's going to be this value right here. What's x? Well, look at the x-axis. X is the concentration. So that's got to be the concentration of A here. That's the concentration of A. Well, the concentration of A is multiplied by something, this value, this slope, and that slope has to be this. The molar absorptivity coefficient times the path length is going to be the slope of your calibration line. Now, we can do that same analysis for compound B. Remember, we did a calibration curve at the same wavelength, and you can see that this also has a slope, and therefore that slope is going to be the molar absorptivity coefficient of B at 550 nanometers times the path length. In this case, that slope is 0.0015. So going back to what I said before, that the absorbance of a mixture is going to be the absorbance of thing A plus the absorbance of thing B. I've changed that equation a little bit. So now I'm saying the absorbance of this mixture at 550 nanometers equals the absorbance of A at 550 nanometers plus the absorbance of B at 550 nanometers. And now we have expressions we can plug in. So what I've done here is, instead of putting the absorbance of A at 550 nanometers, I put what the absorbance of A at 550 nanometers is equal to, according to Beer's law, which is molar absorptivity coefficient times path length times concentration. And then I've done the same thing over here for compound B and the absorbance of B. Well, we know some of these numbers, right? This molar absorptivity times the path length for compound A at 550 nanometers, that was the slope of our calibration curve for A. For B, same thing. These two things multiplied together equal the slope of our calibration curve for B. And we know the absorbance of the mixture. That just comes from the reading we got off the spec when we put our sample in. So we just look at whatever the absorbance is at 550 nanometers, and whatever number that was, that's going to be this thing here on the left. So let's take the numbers that we have and let's plug those in, and we get this equation that we maybe could use to solve for the concentration of A and the concentration of B. The only problem is we have two unknowns. We need to figure out both the concentration of A and the concentration of B. And so if you think back to your algebra, if you need to solve for two unknowns, you need two different equations to use together. So where are we going to get another equation? In this case, what we're going to do is we're going to get a different set of measurements that will give us a second equation. So what we're going to do is we're going to do the same analysis, but we're going to choose a different wavelength. And in this case, I've decided to do it at 500 nanometers. I take the same set of calibration standards, and I take the absorbance at 500 nanometers. I get two different calibration curves. You'll notice that the slopes here are different than the slopes that we had before when we did our calibration curves at 550 nanometers, but that's to be expected. You always have different molar absorptivity coefficients at different wavelengths. And then we can do exactly the same analysis that we did before, where basically we can take the slopes of our lines and say that they equal the molar absorptivity coefficient times the path length. And then we can say the absorbance of our mixture at 500 nanometers is going to be the absorbance of A at 500 nanometers plus the absorbance of B at 500 nanometers. Use Beer's law, plug in our numbers, the slope of the A calibration curve, the slope of the B calibration curve, and the measured absorbance of the mixture at 500 nanometers. And then again, we get an equation that is an expression relating concentration of A and concentration of B. So again, two wavelengths, two expressions containing two unknowns, concentration of A and concentration of B. And what we're going to do now is some algebra. And there's basically a series of steps you have to go through to solve for these, which I've put over here on the right. And we're going to go through those one at a time. So the first one says, use one equation to solve for concentration A. Now, it doesn't really matter which one you pick. You can pick either one of these. And I'm just going to pick the 550 nanometer equation because it's first. So we're going to use that equation to solve for concentration A as a function of concentration B. So here's our equation. We're trying to get concentration A on a side by itself. So basically, we're just going to do a couple of different operations. We're first going to subtract 0.0015 concentration of B from each side, which gives us this. And then we're going to divide everything by 0.0022. That will leave us with the concentration of A by itself on one side, and then this is what we have on the other side. It is a function in terms of concentration B. Step 2 tells us to plug the expression that we just derived for concentration A into the other equation. By other equation, I mean whichever equation we didn't use in step 1. So in step 1, we used the 550 nanometer equation. We derived this expression for the concentration of A. And now, since this stuff right here is equal to the concentration of A, I can plug it into the 500 nanometer equation where it says concentration of A. So here you can see I've basically just taken that expression in blue and plugged it in for the concentration of A. It's now in the parentheses here. Now, you don't have to do it this way, but for me, it makes the math simpler if I say, okay, we're multiplying this whole thing times 0.0015. We're also dividing this by 0.0022. So I just rearranged this. I don't know why that makes my head happy. But then I can use my calculator to solve for this. That's 0.682. And now I can distribute that, multiply 0.682 times the factors in the parentheses, these. So 0.682 times 0.72, 0.682 times negative 0.0015 concentration of B, and I get this. So in step 3, we need to solve for the concentration of B. So here's that equation that I just derived on the last slide. And again, I want to solve for concentration of B. So we first have to get concentration of B on one side and everything else on the other. So let's subtract 0.491 from each side. And we're also going to combine these factors that both contain the concentration of B into one factor. So when we do that, we get 0.279 equals 0.00158 times the concentration of B. And then we can divide by that factor to get the concentration of B equaling 186. So our concentration of B is 186, and step 4 tells us to take that concentration and use it in conjunction with the expression we derived in step 1 to solve for the concentration of A. So again, that concentration was 0.72 minus 0.0015 times the concentration of B divided by 0.0022. So we're going to plug in 186 where it says concentration of B, that should give us our concentration of A, and so that tells us our concentration of A is 200. Okay, so here are the concentrations we figured out. The concentration of A is 200, the concentration of B is 186. What are the units on that? To figure that out, let's look back at our calibration graph, because that's where we got the slope of our line. You'll notice that the concentration here is millimolar. So that's going to be the units on these concentrations. Concentration of A is 200 millimolar, or if you want to put it in molarity, it's 0.200 molar. Concentration of B is 186 millimolar, or if you want to put it in terms of molarity, that's 0.186 molar. Okay, so if you need to find out concentrations in a mixture of colored compounds, which is what you're doing in lab, the executive summary is, first, make a set of standard solutions for each compound in the mixture. What I just showed you the algebra for was a mixture of 2 colored compounds. You could technically do this for 3 or 4 or even more colored compounds, but you would need a set of standard solutions for every single one of those colored compounds. Next, you're going to measure each set of standards at 1 wavelength per unknown. So you're doing a mixture with 2 compounds, so you're going to do 2 wavelengths. If you were doing a mixture of 3 compounds, you would need to measure at 3 wavelengths. The process would still be basically the same. Then you're going to use the calibration curves and Beer's law to set up a series of linear equations. You get to use the algebra, and that will give you the concentrations of your unknown. So again, this is a really useful technique, and it's true a lot of it right now is done by software. One thing we're going to get into is how this gets used in a variety of situations. I start you out with UV-Vis because UV-Vis is the easiest form of spectrometry to understand for people because they can see it. But you can just as easily use this, for example, in infrared spectroscopy. And in fact, that is what people do when they do remote sensing or something like that. So I hope this was helpful, and I look forward to seeing you again really soon.